In this series of videos, I'm going to try to introduce the concepts of imaginary and complex numbers. We start by solving equations.
Okay, hi everybody. So what I'd like to do today is I'd like to start a series of videos where we're going to take a look at imaginary and complex numbers. And this one we're just going to kind of introduce the idea. And I suspect a lot of you are already somewhat familiar with this idea of an imaginary number. Okay, but I want to see if I can give you a little bit more of a foundation. Maybe not, this won't be like the most in-depth thing that you can find out there, but it'll give you a little bit of an idea. So first of all, let's talk about solving equations. Okay, and I'm going to do this in just a couple of different ways here. I'm going to try to come at this idea of imaginary and complex numbers from a couple of different ways here. First of all, if you've got something like this, x squared minus 3 is equal to 0, well, it's very easy to solve that. We're going to bring the 3 over, and then we're going to take the square root of both sides. But because up in this step here we were squaring the variable here, and we know that squaring changes both positives and negatives to a positive, I don't know whether the original value was positive or negative, the square root of 3. Okay? If it's x squared minus 2 equals 0, same thing. X squared equals 2, so x is equal to plus or minus the square root of 2. Every once in a while, though, when we take a look at these things, when we get we'll get a number here that's a perfect square. So when we get x squared equals to 1, when we take the square root of both sides here, we're going to get a nice number showing up here, x equals plus or minus 1. Now, what happens, though, when it looks like this? X squared plus 1 is equal to 0. And so we get x squared is equal to negative 1. Well, here we're forced to take the square root of the negative. Now I'm just going to follow the same pattern that I've established over here. This would be plus or minus the square root of negative 1. But the difference is this. When I take the square root of 3, I can find a real number value that does that. When I talk about the square root of 2, I can find a real number that does that. Now what I mean by that is we can take a look at the number line. Okay? And this is going to be our real number line. And so I put my 0 here, and then I just count out my numbers, right? And everybody's familiar with this. Okay, you learn about the number line way back when. -2, -3, -4, -5. Anyway, here's our number line, and our real number line works like this. Now I can find the square root of 3 on my number line. I can find the negative square root of 3 over here on my number line. Square root of 2 I can find on my number line. Plus or minus 1 on my number line here. And when I square those numbers, I can find the results here. But here's the thing. The square root of negative 1 doesn't show up on this number line. There is no number along the real number line that I can square to produce a negative 1. Which is kind of an interesting result here. So what we do, and I'm sure a lot of you are already familiar with this, what we do is we simply call the square root of negative 1 I. So this would be plus or minus I, and it's I kind of generally accepted to mean it's an imaginary number. Now please don't get confused by that. It's real in the sense that it is a value. It's not real, or it's imaginary in the sense that it doesn't show up on the quote-unquote real number line. Okay, I is not on the real number line. Now what we mean by real numbers, okay, and we'll say it like this. Real numbers can be used for measurements. At least sometime way back when, that's kind of how it was explained to me. Real numbers are used for measurements here of some sort, okay? Think about anything that you might measure, okay, numerically. You use a number from the real line. I mean, negatives can be used to measure, dips below 0 or debt, if you will, stuff like that. We got rationals, irrationals, the whole bit. All those things, though, can be used for measurements. But the square root of negative 1 really doesn't behave like that. It's not a number in the sense that it shows up on the real number line. So now that being said, what I want to do for just a moment here is I want to take a little bit of an aside and I want to take a look at these numbers again with these square roots. Just for a side, then we're going to come back and we'll take a look at the imaginary numbers again, and we're going to see how we can combine a couple of ideas. Okay, so now everybody, what I want to do, just for a moment here, is I want to take a quick look at what happens when you've got a square root. Okay, so what happens when we create numbers that look like this? Actually, and I had to edit that down a little bit here, a bit of a mistake. I'll cover that up there too, just so this is more clear. What happens when you've got a number that's got a square root in it? And you know what? We might have a coefficient and then we can add it to another number. So we're looking at numbers that are of this form right here. And this is about as general as we can make it. And the reason why I express it like this is because oftentimes if you've got a square root here, and I'll give you an example of a number. Let's say this is 5 plus 3 root 2. Okay? This particular value, this is the exact way I would write that. Now, don't get exact confused with precision, okay, precise, because sometimes people want to say, well, no, I can write this more exactly if I convert the root 2 to a decimal and multiply the 3 by the decimal and then add the 5, which is fine in a lot of contexts, but that decimal goes on forever. Okay, so you will never be able to express it exactly with a decimal. You just can't. At some point, you're going to have to stop and round that number, in which case it's not quite the same as this. This is the way to write it exactly. So, you start with a number and then I add some coefficient multiplied by this square root. Okay, in a lot of ways, this radical here kind of acts like an unknown in this particular value here. But this is one number, okay? This is, just one number. Okay, I have to write a couple of terms here to express it. Okay, but it's one value that I'm referring to, and it's one value on the real number line here. But I want to show you what happens when you've got numbers that are in this form. Okay, and it can be any radical you want. But let's say that we're talking about the same radical. So we're talking about all sorts of numbers here that might be like a plus b root 2. Something like that. We can take a look at examples of that in a bit here. But let's just take, for example, that we've got a plus b root c. And then we've got d plus e root c. Let's say that these are the two numbers that I'm talking about. What I want to do for just a couple of minutes here is I want to show you how numbers of this form what we call a field. Now, you don't have to worry about the vocabulary or whatever for right now, but I just want you to see a couple properties here. First of all, I want you to see what happens when you add them. So if I've got a plus b root c, and I add d plus e root c, okay, I'm going to drop the parentheses here. And then what I'm going to do is I'm going to add the two parts here. So I've got a plus d, and then I'm going to have this b root c and this e root c together. Well, I can factor that root c out, and I'm going to be left with b plus e. Together, their sum multiplied by root e. Now, I probably should have stated up here that we want a, b, c, d, and e all to be elements of the reals. Okay? That being said, when you add two real numbers together, you're going to get another real number. So what happens here is when I added them together, I still ended up with a number that looked like this form. Number plus number times root c. Let's subtract. If I take a plus b root c, and I subtract d plus e root c, I'm going to distribute that negative through, but I'm going to then group together the like terms. So I'm going to get a minus d. Then I'm going to get b root c minus e root c, and I'm going to take that root c out, just like I did before, but this time I'm going to get b minus e root c. Now think about this together. Again, the difference between two real numbers is going to be a real number. The difference between these two numbers is going to be a real number. And so what I'm left with is, again, a number that is of the same form. Let's try multiplication. Okay, so I'm going to have a plus b root c, and I'm going to multiply this by d plus e root c. Okay, well, this is going to require a little bit of distribution here. So a times d, so ad plus ae root c plus bd root c. Now, watch what happens here. When I multiply b root c times e root c, I'm going to multiply those square roots of c together. That's going to produce a factor of c. So this is going to be bec there. Now, I'm going to group together the like terms. So AD plus BEC. And remember, when I multiply two real numbers together, I'm going to get a real number. And when you add two real numbers together, you're still going to get a real number. And then I'm going to take that root C out, and I'm going to get AE plus BD multiplied by root C. And look, again, I end up with a number of the same form. Number plus number times root C. Now I'm going to try division. And so I'm going to take a plus b root c, and I'm going to divide by d plus e root c. Now I know I'm kind of really taking my time with this one, and we're going kind of slowly through this, but I really need you to see what's going on here. And understand that every time I apply these operations, I still get a number, or the result is always going to be of the same form as these two values right here. Here, though, when you do division, the way I do this is I'm going to multiply numerator and denominator by the binomial conjugate. So d minus e root c, d minus e root c. Now, I have already seen in the numerator, okay, I already know this, when I multiply that out, it's going to be like the previous step here. I'm still going to do it here. So I'm going to get AD, what is it? There's going to be minus AE root C. Actually, I'm going to try to put these things all together. So this is going to be minus BEC. And then I'm going to get plus. And when you multiply these together, I'm going to get that negative AE and positive BD. So this will be BD minus AE root C. I already knew that was going to work out okay. It's the denominator that I'm a little bit more concerned about. But now these are binomial conjugates, so when you multiply them together, you're going to get d squared minus, and then this is going to be e squared multiplied by c. Now, I've got two separate terms that I'm really isolating here up here in the numerator. And so now, just to simplify this, this is going to be AD minus BEC all over d squared minus e squared c plus b, now I'm going to put parentheses around that, BD minus AE all over d squared minus e squared c, and this is all multiplied by root c. So I know it got a little bit messy here at the bottom, but notice once again, this is going to be a real number, this is going to be a real number, and we are still left with this root c as part of that second term. So when I apply these operations, addition, subtraction, multiplication, and division, okay, to numbers that are of this form, that are both of this form, the results will always be numbers of this form. Now I'm going to do a couple of examples with maybe some numbers with root 2's in them, just to verify that what's going on here is correct. This is important because what we do next with imaginary and complex numbers here relies on this being true. Okay, so here are the two numbers I'm going to work with. 2 plus 5 root 2 and 3 minus root 2. So now what I'm going to do is I'm going to apply the four operations here. So 2 plus 5 root 2 plus 3 minus root 2. Putting that together, because remember I'm going to group together like terms, 2 plus 3 is 5, and then 5 root 2 minus root 2 is going to be positive 4 root 2. And look at that, I get a number that's of the same form as those first two. Let's subtract. Okay, 2 plus 5 root 2 minus 3 minus root 2. Distribute that negative through, so this becomes 2 plus 5 root 2 minus 3 plus root 2. And then I group together like terms. 2 minus 3 is negative 1. 5 root 2 plus root 2 is going to be 6 root 2. There it is again. We still get a number of the same form as the original 2. Let's try multiplication. 2 plus 5 root 2 multiplied by 3 minus root 2. Now multiplication always takes just a little bit more effort here because we got to distribute everything. 2 times 3 is 6. 2 times negative root 2 will be negative 2 root 2. 5 root 2 times 3 will be 15 root 2. And then 5 root 2 minus 2 root 2 is going to be negative, because of that negative, 5 times, well, root 2 squared is going to be 2, so 5 times 2 are 10. Okay, well, 6 minus 10 will be negative 4. Negative 2 root 2 plus 15 root 2 is going to be 13 root 2. There it is again. Same form of value here. And now we'll do one more here. We're going to do division. So 2 plus 5 root 2, we're going to divide by 3 minus root 2. And remember, I do that by multiplying by that binomial conjugate in the denominator. You've seen that before. Okay, well, at least you've very likely seen that before. In the numerator, we just expand it out. So we did something similar up here, but we'll do it again here. So 2 times 3 is going to be 6 plus 2 root 2 plus 15 root 2 plus 10 all over. The denominator is going to be 9 minus, and then root 2 squared is going to be 2. So the numerator is going to be 16 plus 17 root 2 divided by 7. And now I'm going to distribute the 7. So this becomes 16 over 7 plus 17 over 7 root 2. And once again, there we go. It's a little bit more complicated this time, but it's still of the same form. Now, before I totally leave this, what I want you to recognize about this is each one of these numbers here and each one of the results is going to be represented, okay, by a value on the number line, on the real number line. A single value, okay? 16 sevenths plus 17 sevenths root 2 is going to represent a single value on the real number line. I should write that down here. Each of these, okay, represents a single point or value on the real number line. Okay, that's a really significant point that we want to make. Okay, everybody. So there's one more thing that I want to take a quick look at before we kind of put things together and try to understand what these imaginary or complex numbers are here. And I want to talk about multiplication. Just simple, straightforward old multiplication. And to do that, I'm going to go back to the number line here. So when we take a value and multiply it by another value, okay, what we do is we change its magnitude. And the magnitude of a number, okay, is always measured by its distance from the zero. Okay, that's just what it is, right? This point over here is 2. Why? Well, because it's 2 units away from the 0. This is 3 units away from the 0. This is -1, this is -2, but only negative because that just simply means to the left. Okay, we understand that negative means to the left, positive means to the right. Okay, multiplication, okay, multiplication changes the magnitude. Okay, so if I've got 1, for example, if I multiply 1 by 3, that simply changes the magnitude. That's it. Now, if I multiply 1 by 1/2, again, it changes the magnitude. Multiply it by root 3, it changes the magnitude. However, there is a number that doesn't change the magnitude. Okay, when we multiply by -1, the direction changes. Okay, the direction changes, and really important, not the magnitude. Whoops. Oh, okay. Well, it's going to look like I spelled that wrong. I'll fix that. Okay, it's going to look like we multiplied, we changed the direction here, not the magnitude. Now, what I mean by that is if I've got 3 and I multiply it by -1, I jump to -3. Now I'm still 3 units away from the origin. It's just that I'm pointed in the opposite direction. So in essence, what that did, okay, was it caused, if you want to think of it like this, okay, if I start here and I'm going to do it like what we call a vector here. I'm going to draw a little arrow here. Okay, if I take and multiply 3 by -1, what that does essentially is rotate that vector 180 degrees. Okay, so when we multiply by -1, we get a rotation of 180 degrees. It changes the directions. We move in the opposite direction. Okay, that's what the negative does. Now, every other number that we multiply here, every other real number that we multiply by, is going to end up changing the magnitude. As soon as you throw the -1 in there, it changes the direction. Now, you might say, well, what if I multiply by -3? Doesn't that change the direction as well? Yeah, but then we would tend to think of that as you multiplied by 3 and a -1. We would tend to separate that -1 from that. Okay, so I hope that makes sense, because now what we're going to do is we're going to take a look at, well, wait a minute, what happens when we use this other number? This number that we just introduced at the beginning of this video here. So here's my number line again, 0, 1, 2, -1, -2. And then we introduce this I. And we know that I is the square root of -1, and we know that I does not show up on the number line. It's not on the real number line. It doesn't show up anywhere. So where is it? Well, let's think about how it behaves. Whoops, sorry about that. If I multiply, if I multiply 2, okay, by -1, that rotates around 180 degrees and points me down to -2. Now, I is the square root of -1. So for me to get the same result, I'd actually have to multiply by I twice to get that -2. This I squared would become my -1. I by itself isn't going to give me that negative. I need to put 2 of those together. So what that sort of implies is that, now bear in mind, I should backtrack here before I say this. Bear in mind here that because it's related to the -1 here, this is going to affect the direction, not the magnitude of the value. Okay? Like when I multiplied by 2 i's, I didn't change the magnitude of the value, I simply changed the direction. But notice I had to do it twice. So because it's related to the negative, it's going to affect the direction. But I needed to do it twice to get the full 180 degrees. Multiplying by I is like rotating. Well, if doing it twice gets me 180 degrees, doing it once creates a rotation of 90 degrees. So when I multiplied by I, instead, okay, here's 2. When I multiply by I, that's basically got to be going in this direction, so 2i. Multiply by another I, and that gets me the full rotation, 180 degrees. Now this is interesting. Okay, this is really, really interesting, because now this gives us a sense of what I is. Okay, it's this other, now I don't want to say dimension here, because that's going to, I don't want you to get confused with the Cartesian plane. Okay, I really don't want you getting confused with the Cartesian plane here, although there are some similarities, there is a difference here. But when I multiply by I get this rotation 90 degrees, it starts to point out perpendicular to that real axis there. Okay, so I exists out here. Now, I want you to get what's going on though. So now what I'm going to do here is I'm going to create a a complex number. Okay, so had just spent a little bit of time talking about numbers of the form a plus b root c. And now I knew from the beginning here that I was equal to the square root of a number. So now what I'm going to deal with specifically with numbers that look like this, a plus bi. But now this is going to mean something a little bit different to me. Okay, so what I'm going to do is I'm going to take a, okay, so some number along the real axis here, and I'm going to add to that b multiplied by I. Now remember what I does, I rotates it 90 degrees, so I'm going to actually be somewhere up here. Okay, now with the real axis, it didn't do that. When I had like say 3 and I added 4 times root 2, it was just affecting the magnitude of the number, so all I was doing was moving back and forth along the real number line. But this does something a little bit different. This causes that rotation of 90 degrees. So now I'm pointed out in this direction here, which means, okay, now, and bear in mind, this is the really cool part of this. This is still one number. This is still one number. Just like I had said before, you're going to notice when we were back here talking about all these things here, whenever we did those operations and we got these values like this, remember this all represents a single number on the real number line. Here, this is still going to represent a single number. But the only way that I can fully understand it is by understanding it on this plane. Okay, so now what I've got is I've got this real axis. Okay, here's my 0, 1, 2, 3, -1, -2, -3. And then I'm going to have this imaginary axis going up and down. And remember, the I simply causes a rotation, but I can rotate any number I want up 90 degrees. So I'm still going to have 1, 2, 3, and this will still be -1, -2, -3. But this right here, for example, this value here, which is 1 over along the real axis, so that would be my A, 1, and then 2 up along the in the imaginary direction here is going to be 2i. That number right there, that is a single number. On the Cartesian plane, that's two numbers, okay? It represents a relationship between x and y. That's not what this is. This is a single number that requires two different parts to represent completely. This is why we call it a complex number, okay? Because it requires two pieces. Okay, it requires two pieces, and one of them is very different than the other ones here, okay? So this is a complex number. It requires these two pieces to put together here to express completely, okay? So again, it's not a number. It's not a point necessarily on the Cartesian plane, okay? Instead of now having a number line, we have a complex plane that represents a whole bunch of single numbers, which is a little hard to get your head wrapped around, but at the same time, everything works together beautifully to imply that that's what's going on. I absolutely love this material, okay? So now what I want to do here is I want to do some examples with you of just some of the operations that work with complex numbers. Okay, now I don't want to do too much more in this particular video lesson. It's going to start to get a little bit out of control. But we'll come back and we'll talk a little bit more about some of the properties here and whatnot. All I want to do right now is I want to just show you how the operations work. So let's take a look at addition. So here are my two complex numbers here. Okay, remember the complex numbers have a real part and an imaginary part to give us one single number here. So we'll go 3 plus 4i and we'll add 2 minus i. Okay? And when we add those together, we simply add the real parts to get 5, and then we add the imaginary parts here, 4i minus 1i, and we'll get 3i. Okay? That's it. And actually now I tell you what, I should just for a moment here, we should just kind of sketch these two. 1, 2, 3, 1, 2, 3, 1, 2, 3. I got to go 4, 1, 2, 3, 4. So this first one here, which was 3 plus 4i, will be 1, 2, 3 along the real axis, and then 1, 2, 3, 4. That's out here. This right here is 3 plus 4i. Okay, 3, and then I'm going to add 4, but I'm going to rotate that 4 90 degrees to the real axis. 2, right here, minus i. So I'm going to take the negative 1, okay, and I'm going to rotate that along the, so I'm going to multiply by I and rotate it along, rotate it 90 degrees, but then negative 1 drops us back. So then we're down to here. So right here, this is my 2 minus I. Now you're going to see frequently that they're going to represent these with vectors, okay? Where we're going to point those out like that. And we'll talk about that later. Okay? But for now, make sure you understand that, and that all we're doing right now when we add is we're just going to add the components together. To subtract, it's the same thing. 3 plus 4i. We're going to distribute, so 3 plus 4i minus 2 plus I. So 3 minus 2, because we're going to combine the real components, will be 1. 4 plus I, 5i. Now let's multiply. 3 plus 4i multiplied by 2 minus I. And this really shouldn't take anybody by surprise here, because we're just going to go right back to like the original, or one of the first things we said in this video about the nature of I. When you distribute this, 3 times 2 is 6. 3 times negative I will just be negative 3i. I mean, we treat it like it's a variable for the most part. 4i times 2 is going to be 8i. But here's where it's different here. 4i minus I is going to be negative 4i squared. Now, that's going to be 6. And then when I look at how many i's I have here, well, negative 3i plus 8 is going to be 5i. But this right here, negative 4 times I squared, well, I squared is negative 1. So it's going to be positive 4. And so our answer here is going to be 10 plus 5i. That's our answer. And then I know what that means. I go 10 along the real axis. I'm going to multiply 5 by I, which rotates it 90 degrees. I'm going to go up 5. Now let's do division over here. I don't want to move on to another page here. So division, let's say I've got 3 plus 4i over 2 minus I. So once again, to do this, I'm going to multiply by the conjugate. Okay? I mean, that's how I did it all with those roots in there. Okay, and remember, the I is just a radical. So this is just exactly the same form as that A plus B root C. So 3 times 2 is going to be 6. This is going to be 3i plus 8i plus 4i squared all over, and then the denominator is going to become 4 minus I squared. So 6 plus 11i minus 4, because that I squared, and then down here this is going to be 4 plus 1 because of that I squared. So now I've got here's 2 plus 11i all over 5. And now I'll just distribute that denominator to both of those terms here. So 2 fifths plus 11 fifths I. And those are the basic operations with complex numbers.